We have a couple of things to talk about in this lecture. The first of which is power, and by definition, power is just work over a time interval. So it's the time derivative of our work. So that's one way to think of power, is dW dt. I can rearrange this a little bit by plugging in our definition for the work, which is F dr by dt, and then rearranging, I get F dot dr dt, and of course dr dt by definition is velocity. So power can also be described as the dot product of force and velocity. So it's a time derivative of work. It's also force times velocity. I can use that to figure out power. So this is also a scalar, just like work is. So it has no direction, just a magnitude. It has units of joules per seconds, which is a watt, or foot-pounds per second, or a lot of times we call that horsepower, where 1 horsepower is 550 foot-pounds per second. Okay, so again, it's just work per time. Okay, now we can talk about efficiency. We can talk about this in either terms of power or in terms of work. And in engineering, we always call efficiency basically the output divided by the input. So the output power versus the input. So if you think about like an automobile, how much power I get out versus how much in potential power I can get from the gasoline that I'm burning. Okay, so this efficiency always has to be less than 1 in order to obey the laws of thermodynamics. So efficiency will always, you'll never get out more than what you put into something. Okay, so that's power, pretty straightforward. Again, just time derivative of work. The other thing we want to talk about is the conservation of energy. In order to do that, we need to first talk about a conservative force. And a conservative force is basically a force that's independent of the path that it follows. Basically, it only depends on the initial and final positions of the object. So two classic examples of this are gravity as well as spring. Okay, because again, gravity only, going a little deeper into gravity, it only acts downward. So the fact that I might go up a hill horizontally as well as vertically, again, the work due to the gravity only depends on the vertical point. It doesn't really matter, how it got to that point, whether it's straight up or up at an angle. Again, gravity only is concerned with its initial and final position. The path is unimportant. Okay, so within this conservative force, we're going to define something called potential energy, which is basically the conservative force's capacity to do work. Okay, the potential work that's capable of a potential energy, or a conservative force, such as gravity or spring. So let's look at gravity, and potential energy is basically defined as its weight times its position from some datum point. And I get to define my datum point. So if I'm above my datum point, I have the potential to do positive work. So we call that a positive potential energy. That is, gravity can pull this down back to the datum in the direction of gravity. So that would be a positive work. So it has potential to do positive work if it's above the datum. It has potential to do negative work because, again, to get it back to the datum, it has to oppose gravity, go in the opposite direction of the weight. So if it's below the datum, we call it negative work because, again, it has potential to do negative work to get it back to datum. And again, it's just that weight times the vertical distance. Okay. Now, a spring, its potential energy is defined, as its potential to do work, which is 1/2 ks squared, which is the work of a spring. Okay. Now, this is always going to be positive. Okay, and the reason for that is, well, not only because I've got this s squared, but if you think about this, okay, if my particle is moved in the positive s direction, okay, to pull it back to datum, the unstretched length, okay, the force is going to pull it to the left, okay, so the force and the displacement back to datum are in the same direction. Similarly, if I compress it in the negative s, okay, to get it back to datum, it's going to push it to the right, okay, and move it to the right. Therefore, it has potential to do positive work to get back to datum. So a spring's potential energy is always positive. A gravity's potential energy, if it's above the datum, is positive. If it's below the datum, it's negative. Now, if I have only conservative forces on a system, we can say that our energy is conserved. So, for example, if it's only springs and gravity, Okay, if I have some sort of external force that I'm pushing on it with, or if I have friction, these are things that are non-conservative. So if only springs and gravity are acting on it, I can say that energy is conserved. And what I mean by that is the initial kinetic plus potential energy equals the final kinetic plus potential energy. So the total energy, kinetic plus potential, remains constant throughout the entire system. Okay, and that's only if I have conservative forces such as gravity and springs is energy conserved.